Hello everyone, what I want to do in this video is to take you through the successive over-relaxation method in numerical analysis. So sit back, relax, and let's simplify. With authorization from the school, a computer science class sets out on a mission to assist its deferred course by debugging codes for cash. They must utilize the earnings from this business to cover their course tuition. The class debugged 7 codes in Python, 17 codes in Java, and 3 codes in C++ for a total of 500 Ghana cedis in the first week. In the second week, they debugged 12 codes in Python, 11 codes in Java, and 24 codes in C++ for a total of 750 cedis. Moreover, the class debugged 28 codes in Python, 21 codes in Java, and 5 codes in C++ for a total of 1000 cedis in the last week of the month. Represent the above in systems of equations. Solve the above system of equations using the successive over-relaxation method with your solution accurate to either epsilon equals 0.01 or the if iteration. Note, solve with the appropriate initial condition and omega value assigned to the various groups in the attached sheet. Alright, so we know that the value for omega ranges from 0 to 2, meaning we can choose any value between 0 and 2, with 0 and 2 inclusive. So to represent our system of equations, we have 7 codes for our x, 17 codes, that's going to be our y, and 3 codes will be our z, equals 500. So 7x plus 17y plus 3z equals 500 for our first equation. Our second equation will be 12x plus 11y plus 24z equals 750, and our last equation will be 28x plus 21y plus 5z equals 1000. So that will be our systems of equations. Now the main problem is, how do we solve this system of equations with the successive over-relaxation method? Now to do this, I would like to take you through a sample question that we are going to use to model how to solve this main question. So let's get to that sample question and see how that question goes to get an understanding of how successive over-relaxation method actually works. So let's get to that particular question or that sample problem. So solve the following system of equations. From the previous problem, we were able to derive our system of equations. So we are going to get something like this for our systems of equations. And then again, we've been given some initial solutions to be 1, 1, 1, and then omega to be 1.25, and then epsilon to be 0.01. And we are asked that we can either get to epsilon or stop on our fourth iteration. Alright, so what we are going to do now is that from our LU decomposition, when we were using the direct method from last semester, we knew that AX is equal to B for our A matrix, and that we knew that A was equal to LU. But in the successive over-relaxation method, what we are going to do is that we are going to have the A part be L plus D plus U times X equals B, where the L plus D plus U is the matrix A. Now we know that this A portion is now being represented by L, D, and then U. The L is the lower triangular matrix, D is the diagonal matrix, and then U is the upper triangular matrix. Now from the formula we have on top here, L plus D plus U all times X equals B, with the successive over-relaxation method, we are going to multiply through by the omega. So the omega is this sign we have over here. Now with this omega, what we are going to do is that we have the omega times L plus omega D plus omega U all times X equals omega B, that we've multiplied through by the omega. And then one technique which is used in the SOR method is that we add and subtract dx, that is the diagonal matrix. So dx minus dx, it actually does nothing though, because you know that dx minus dx is actually 0. Alright, so we are going to make one of the x the subject. Now to do this, we have to do some manipulations here. We are going to multiply through by the x as we have here. You multiply through by x, and then when we have omega lx plus dx equals what we have here, we now factor x out, And when we have x outside of this omega lx plus dx, we are going to divide through by the omega l plus d from here. So you can see that we have expanded this part, and at the top here we have factored the x out of this expression, and then we're going to divide through by the omega l plus d. Next up, when we divide through by the omega l plus d, we are going to have the inverse of omega l plus d, meaning 1 over omega l plus d, multiplying this whole thing here. So we've actually factored it out in a very special way. Let's take it from the top here. We said we're dividing through by the omega l plus d, so we have omega b here. So this omega b has been divided by the omega l plus d, as you have here. So you can see this portion here, omega, then we have d plus omega l inverse times b. So that is what we have here, is omega b over omega l plus d. That's what we have over here. And then this whole portion here, negative omega ux plus 1 minus omega dx, we have taken this whole thing here and then divided by the omega l plus d. So as you can see here, we have the whole thing over here and it has been divided by the omega l plus d. Right, so we are dividing everything here by the omega l plus d. We are dividing here too by we are dividing the omega b also here by the omega l plus d. So now we have our main formula. Now the formula we'll be using now is what we call the k1, the k formula. So you're going to have xk plus 1. Then anywhere you see x, you put a k over there. So we're going to start. So with the k, we are going to start our iterations from a value k, and the k starts from 0, 1, 2, and then it goes on. So you are seeing an xk plus 1, which we know that the k will be starting from 0. And then anywhere you see the x, you can see there's a k over there. So as you go along, you understand how this thing actually works. So now let's go back to the equation and draw out our matrix A. So our matrix A is going to do something like this: 21, negative 2. Remember that we are drawing the matrix A from the systems of equations here. And then we can find our B. Our B is going to be 17, negative 8, negative 18, and 25. So that's our B, 17, negative 18, and 25. And then next will be our L. We know that L is a lower triangular matrix. Its trivial values are at the lower side of the matrix, and the upper parts are all zeros. So we are getting it from matrix A, which is 3, 2, and negative 3. That's the lower part of matrix A. And again, we find for our upper triangular matrix. We know that its trivial values are at the upper side of the matrix, and then again we are getting it from the matrix A, which is 1, negative 2, and then negative 1. And you see that the down parts are all zeros. And then lastly, we find D. D is the diagonal matrix. So look at matrix A, look at what says diagonal. You pick the diagonal and then you make the other entries all zeros. So now we've been able to decompose our matrix A into its components L, D, and then U. So now that we have all our components in check, we are going to use this formula in red, the one here, xk plus 1. And then we know that we have all our values for omega. We know omega, we know L, we know D, we know U, we also know B. So it means we can use this formula here to find x1, y1, and z1. We also know the value of k, that k starts from 0 and then it moves to 1 and then it moves to 2. So when we are starting k from 0, that means you're going to be finding for x1, and then finding for x1 we'll find for y1 and then y2. We also know that the values for x starts, the initial values are 1, as you can see here. So when we get xk, which will be x0 is going to be 1 because the initial values are 1. So x0 will be 1, but then we'll be looking for x1. So as you go there, you understand more. So now let's use this formula in red to find the value of x1. Since you already know x0 or x0, we know that x0 is 0. Sorry, x0 is 1, but we don't know the value for x1. So we're going to find the value for x1, y1, and then z1. So let's get there. Using the formula above as I indicated earlier, now we are going to find for omega L plus D inverse. Because there are a lot of matrices involved, we want to solve them individually so that we can better comprehend it. So to find omega L plus D inverse, let's go to our calculator to do some computations.
Alright friends, so on our calculator, we are going to go to the matrix mode since we'll be dealing with two matrices, L and then U. Sorry, L and then D. That is the lower triangular matrix and the diagonal matrix. So let's go to, you put your calculator on, then you go to mode. So with the mode, you choose number 6, which is the matrix. So you press number 6. And then what you do next is that you choose matrix A. So you press on 1. Then from there, you choose a 3 by 3 matrix. So another one. Then with the 3 by 3 matrix, the first matrix we are taking is the lower triangular matrix. So we are going to make the entries for the lower triangular matrix in the 3 by 3 matrix A over here. So we have 0, 0, 3, 0, 0, and then 0, and then we have 2, 2 here. We have -3, and then we have 0. So these are our entries. As you can see, okay, I made a mistake here. At the top here is supposed to be 0. Alright, so as you can see, we have our entries here for the lower triangular matrix 3, 2, and then -3. So when you are done making your entries, you press AC, and then you clear it. Then again, you press Shift +4 for the matrix. Then you choose data, that's number 2. Then you choose 2 again, that's matrix B. Then you choose a 3 by 3 matrix for the diagonal matrix, so 1. Then now you make the entries for the diagonal matrix. So again, as you can see here, you can see that I've inputted or I've made the entries for my diagonal matrix. So we have 20, 20, 20 for the diagonal, as you can see. So again, what you do is that you press AC to clear on your calculator. Then once you clear for the AC, what you want to do is that we want to find omega L plus D or inverse. We know the value for omega to be 1.25, so 1.25 brackets times matrix A, which is the lower triangular matrix. So Shift +4, and then you choose matrix A, which is number 3, right? So matrix A, then plus, and then the matrix B, which is the diagonal. So Shift +4, and then the diagonal matrix, which is matrix B, so 4. Right, now the inverse of all of this, so we bring a bracket here. They bring a bracket to at the initial part. You put another bracket over here. Then at the last part, you press this one, sorry, the value over here to make it an inverse. So as you can see the inverse, so I'm going to press equal to on the calculator, and you can see that I have my values there. So I think 0.05, 000, -9.63, 0.05, 00, and then up to 0.05. So this is my value for omega L plus D all inverse.
So back over here, I'm going to put my values over there. So as you can see, I've equated omega L plus D all inverse to the value we had on the calculator. Next up, we find the one in the square braces over here. So 1 minus omega times dx0 minus omega u x0. Remember that we are using k equals 0. That's why we have the x0. And we know that x0 is actually equal to 1. That's the initial value if you remember. So now let's find 1 minus omega times dx0 minus omega u x0.
So over here on our calculator, what we're going to do is that we are going to press on mode, then again matrix, which is number 6, then choose matrix A, and then a 3 by 3 matrix for the diagonal matrix, so 1. Now you put in your values. So we know that the values for D or the values for it are 20. So let me do it here. Alright, so you can see my values for the diagonal matrix. So 20, 20, 20 for all of them here. So I'm going to press on AC to clear. And again, I'll press on this one plus 4. And I'm going to go to data. Then the data, I'll choose matrix B, which is a 2. And then I'll go to 1 for a 3 by 3 matrix. We're looking for the upper triangular matrix. So I'll put in the values for the upper triangular matrix. You make the entries for it. So as you can see, I've made my entries for the upper triangular matrix. That is 1, -2, and a -1. So after you make the entries, you press on AC and then you clear. Now you go to the equation that we had. So I'll press on. So we can do this. We have 1. The equation was 1 minus omega. So bracket 1 minus omega is 1.25. Then bracket. Then we have D. D is the matrix. D is matrix A. So shift plus 4. I'll get matrix A by pressing on 3. That's matrix A. Then bracket. Now x naught. X naught is 1. So I'll put 1 over there. Now minus omega. We know that omega is 1.25. So 1.25. And then bracket. Then I have matrix B, which is the upper triangular matrix. So shift plus 4. Matrix B will be 4. So I get it, and then I close my brackets. Then times x naught. X naught is 1. So times 1 here. Now I'm going to press on equal to get my answer for it. So as you can see, we have -5, -1.25, 2.5, -5, 1.25, -5, 4, and the other here are all zeros. So this will be our value for 1 minus omega times d x naught minus omega u x naught. So let's go back to our presentation.
So this will be the values we had from our calculator for the second term. You can see we have 3 terms here: term 1, term 2, and term 3. So this will be the solution for the second term as we had from our calculator. Now to the third term we have, that is omega d plus omega l inverse times b. So again, we are going to go to our calculator to find for the values here. But before we go to our calculator, be reminded that we have already solved for d plus omega l or inverse at the top here. So we're going to take this one as one matrix and then take the b here also as another matrix. So we'll be reminded that we have already found d plus omega l all inverse from the top here. So we will take this matrix and then multiply it by b and then the omega to find the value for this one. So let's get back to our calculator.
Alright, so back on our calculator with the solution for the third term, you select mode, then you choose matrix, then matrix A as we've been doing before, and then a 3 by 3 matrix for the one in the brackets. So we're going to make the entries as we have already made this before. So I'm going to make the entries for the matrix A. So these are my entries for the matrix A. Be reminded that we are using the omega L plus D all inverse. We have already found it. So we are just inputting it and then we find the B also. So as you finish, you press on AC and then you go to shift plus 4 and then you choose data and then you choose math B. Now be reminded that B is a 3 by 1 matrix, not a 3 by 3 matrix. So you select 3. Then you put in the values for B. So these are our values for B. So we have d plus omega L all inverse, and we also have b, and we already know the value for omega. So now let's go ahead to solve the formula that we had. To do this, let's press clear. Now with the formula that we had, we know that omega is 1.25. So I'm going to write down the formula here. So as you can see from here, omega is 1.25. Then the math A, which was the d plus omega L all inverse, then times b, which was the math B. So we are multiplying them here, and I press on equal to. So you can see the values that we have: 1.0625, -1.324, 1.181. So that will be our solution for the last term. So let's get back to our presentation.
So here on the presentation, let's write out the solution we had from the calculator. So you know that omega d plus omega l all inverse times b will give us 1.0625, negative 1.324, and then 1.181. Now that we know all the values for the terms, term 1, term 2, and term 3, we can now find the value for x1. Now we know that we can find the value for x1. Now to do that, we are going to multiply the first term by the second term plus the third term. So that's how we are going to do it. So we take the first term plus first term times the third term plus, so first term times the second term plus the third term. So these two, we multiply them plus this term. So to do that again, let's go to our calculator to multiply these two terms. Then after that, we add this term to it. So we are going back to the calculator again to multiply these two matrices.
So back on our calculator, we want to multiply the first two terms and then add the third term to them. But you know the calculator can take one at a time. So let's do that. We are going to multiply the first two terms and then add the third term. Now we are going to take it very slow. So let's now just multiply the first two terms and then later you add the third term. I'll tell you the reason why I'm doing that. And I know most of you are getting errors at this place. The error is called dimension error. When I get there, I'll explain why I'm taking it very slow here. So let's go to mode, then choose matrix, then choose one, a 3x3 matrix. Now I'm going to input the values for the first term. So now I have made the inputs for the first term that we had. Now the next thing to do is that we are going to take the second term and also make the entries for it in Mat B. So I'm going to clear from here, then choose Mat B. So go to data and then choose 2, Mat B. Mat B is also a 3x3 matrix, so 1. Then I'm going to make the entries for that one. So as you can see here, I've made the entries for the second term. Now what we are going to do, we're going to multiply the Mat A and then the Mat B. So I'm going to clear, then choose Mat A, which is 3, times the Mat B. Now those of us who are getting the errors, you might be in a rush that why don't you just add the third term? When you add the third term, you're going to get a dimension error because you can't add a 3x3 matrix to a 3x1 matrix. So this is why most of you got the error. When you get here, take it slowly, take it one at a time. Do the multiplication before you do the addition. So we are taking it slowly, we're just doing the multiplication, then we come back later to do the addition. So that will be the last part. So when I click on equal to, this will be our solution for multiplying the two terms. So I'm going to put it on the presentation. The last part will be we adding the 3x1 matrix.
So from the solution that we had from the calculator, I just wrote it out here, as you can see down here. So negative 0.25 and the last was negative 0.258. So this is where you have to be very careful. You can't do this on a calculator. So you can't do this using the matrices on a calculator because we're getting a dimension error. So what we're going to do is that this value we have, which is the third term here, we're going to add it as vectors. So as you have it here, you're not going to add them as matrices but as vectors. So you add everything on the first column, so on the first row, then add everything on the third row manually, and then add everything on the third row. When you add all of them, then you're going to have your x1, y1, and then xz1. So this will be our final solution for x1 0.8750, y1 negative 1.4766, and then z1 0.9263. So as I said, don't add them as matrices on the calculator. If you do that, you'll be getting dimension error. Add all of them manually as vectors. So you add everything on the first row, add everything on the second row, add everything on the third row, and then you'll be getting your x1, y1, and then z1. However you write it, you are right. So now that we have x1, y1, and z1, the question says we should solve it to the fourth iteration, or to the state where epsilon value is 0.01. So to do that, that's going to require a lot of time and going to make this video very, very long. So what I'm going to do is that now that we have x1, we go back to the formula that we had. So what we are doing here is that when we get back to the formula, you can see our second term here. We have x0. This time we have x1. So where you see the x0, you put the value for x1 over there, which is 0.8750. Where you see the x0, then you find this term. When you get that term, multiply the first term by that second term plus the third term you have over here. When you do that, you're going to get the values for x2, y2, and then z2. Then you check, is the difference between x0 and y1, is the difference between them is less than 0.01. If not, you do another iteration. And then now that you have x2, put the value of x2 where the x0 is here. At that time it will become x1, so put the value of x2 where the x0 is. Then find for the second term. When you get the matrix, multiply the first term by that second matrix plus the third term over here. When you do, you're going to get for x3. When you get x3, the value you get for the x part, the x3 part, you get x3, y2, y3, and then z3. You take the value for the x3, put it where the x0 is. You see where the x0 is, you put it there, get a value for this matrix, and then multiply the first term by the second term, and then add this third term to it. You're going to get a set of x4, y4, and then z4. Now the iteration keeps on, but the question said we should end at the fourth iteration. So when we get to the fourth iteration, the value should be getting for x3 or x3 or x4, y4, and then z4. That will be your final solution. So, and again, you can be checking the stopping criteria. Check the difference between x0 and x1. If the difference is less than 0.01, check the difference between x1 and then x2. If the difference is less than 0.01, check the difference between x2 and then x3, like that, as you get your values, or until you get to the fourth iteration. So that's basically it. You keep doing these iterations until you get to either the fourth iteration or get to a point where the criteria or the value of epsilon, the difference between the x values, is less than the epsilon value, which is 0.01. I think I've been talking a lot and I'm making the video too long, so I'm going to end over here. And always be reminded that you put the value for the x, just the x value, where the second term is, and then you find your second term where the x0 is, and then you find your second term, you multiply them and add the third term to it. So alright friends, so don't forget to show some love by hitting the like and subscribe button. I hope you have learned something today. If you have any questions, don't be shy to leave it in the comment section. I'll be willing to reply you. And again, show some love, hit the like and subscribe button. Until next time, apatia.